Okay, the last example for this lesson is going to look at algebraically how we solve two-dimensional vector displacements. Okay, so we have a person drives 120 kilometers north, 32 degrees west, in a car to a friend's place to visit, and then drives 150 kilometers west, 24 degrees north to visit family. Determine the total displacement of the trip in kilometers. Okay, so remember, what I always kind of like to do in terms to get what we have to do here is we have to break down both of our vectors, or both of our displacements, into their respective vector components. Okay, so what I like to do for each is, well, our directions are north and west here that are considered for both. So I'm going to draw two little quadrants here that represent the direction of north and west for both my displacements. Okay, this just gives me a chance to draw both vectors the way they are represented here in 2 dimensions to see where the angle lies and which x and y components are going to be either sine or cosine. So for this one, remember, we're going north and then 32 degrees towards the west. So your displacement vector gets drawn in there where this is 32 degrees. So if we want to use this respective 32 degrees, then this right here is your x component for that first displacement. This right here is your y component for that first displacement, and we know that this magnitude is 120. So it becomes a lot like that problem you guys saw today where you have to solve for those side lengths, except this time we actually have the hypotenuse with an angle. So we can use, in this case, opposite that angle is x, so we're going to use sine to determine x. Adjacent to that angle is y, so we're going to use cos to determine y. Okay, I do the same thing with my second displacement in that second quadrant. Okay, so this time we move west and then 24 degrees towards the north. So your second displacement, obviously not drawn perfectly to scale, is going to lie somewhere in there, where this is your 24 degrees. So now if we want to enclose that angle with the sides of our triangle, this right here is going to become your x component, where this right here is going to become your y component, and we know that the magnitude of this is 150 kilometers. So again, you're going to use your sine and your cosine, but notice this time it switches. Because y is opposite your angle, I'm going to use sine to determine that y component, and because x is adjacent to that angle, I'm going to use cos to determine that x component. So let's do the respective displacements. So displacement 1 in the x direction is going to equal 120 kilometers times, we're opposite that, so we're going to do the sine of 32 degrees. Okay, and that will give us our x component for that vector. So if I type that into my calculator, I get 63 point, I'm going to carry a few extra decimal places and then I will round to significant figures in my final answer. It just keeps the answer a little bit more accurate. So 63.5903 kilometers. And remember, this is your x component, so always get into the habit of labeling that direction that is with your x component. This is in the west direction for that displacement. Okay, the y component for our first displacement, well, we used sine for x, so we're going to use cos for y. So we have 120 kilometers times the cos of 32 degrees is going to equal, for this one I get 101.765 8 kilometers, and that component is in the north direction. Okay? Then we do the exact same thing with our other displacement vector. Remember, we just switched the ratios that we're going to use. So for x, we're not using sine this time, we're using cos. So you get 150 times the cos of 24 degrees. Excuse that banging, that is my dog. 150 times the cos of 24 degrees gives me 137.0318 kilometers. Again, this is in the west direction. And then the y component is going to be 150 kilometers times the sine of 24 degrees. Okay. So 150 sine 24 equals 61.0105 kilometers, and again, your y component for that second displacement is north. Okay, so now remember, what you want to do to get that total displacement is you're allowed to add x components to x components and y components to y components. So for that total displacement in the x direction, we're just simply going to look at taking the displacement 1 in the x direction and adding displacement 2 in the x direction. Okay, so this was 63.5903 kilometers west plus 137.0318 kilometers west. Okay, once we add all that together, I end up with 200.6221 kilometers west. Okay, same thing for the y direction. You're simply going to add those total y components, or the two displacements in the y direction together, to get the total displacement in the y direction. So I'm taking d1y plus d2y. So d1 was 101.7658 kilometers north plus 61.0105 kilometers north. Okay. When we add all this together, I get 162.7763 kilometers north. Okay? Now, recall, once you've broken down the vectors and got the total x and y components, now we can put those back together. So now we have an x component that is roughly 200 kilometers. Oops, sorry, that's totally in the wrong direction. Let's just switch the direction of that vector. We're going west. So you have one that's roughly 200 kilometers in this direction, and one that's roughly 163 kilometers in this direction. So we are now looking for this total displacement vector here. We need the magnitude of it, as well as the angle here that is created by those two vectors. So remember, once you've broken it up by sine and cos, we use Pythagorean theorem to get the magnitude, and then we use tan to get that angle. So to get the magnitude of that total displacement vector, you're taking the square root of the magnitude of the total displacement in the x direction squared plus the magnitude of the total displacement in the y direction squared. it looks like is we have 200.6221 kilometers squared. Remember, I've dropped the direction now because I'm just looking at magnitude. We only care about the size of the total displacement vector in this case. Your y component was 162.7763 kilometers squared. Okay. So when I square those values and add them together, we end up with square root of 66,745.35085 kilometers squared. Take the square root of that value, and that will give us the magnitude of our total displacement vector. So I end up with 258.3512 kilometers. And then we want to find what that angle is. Okay, so remember, to find that angle, we're taking the tan of the opposite over the adjacent. Okay, what you'll always see me do is I like to always just do the tan in one way, and then if your angle ends up being larger than 45, then we will just flip the two directions that are involved and use the complementary angle. Okay, so if you always use theta as the tan inverse of your y component over your x component in the total displacement vectors, that's always going to compare it to the horizontal first. So most likely your east and west direction, whatever the horizontal is in that case. Okay, so if you always do dy over dx, then you're always going to end up comparing that horizontal direction first, then the angle, then the vertical direction. Okay, so we're going to take the tan inverse of the y component was 162.7763 kilometers. The x component was 200.6221 kilometers. Okay, your kilometers cancel out, leaving you with just a value. So when we type that into our calculator, we get an answer of 39.05 degrees. Okay, so the nice thing is because that is less than 45, we don't have to worry about using the complementary angle. Say this came out to something like 59 degrees, then what you would end up doing is finding the complementary angle of that, which is obviously 31, and then instead of listing the horizontal direction first, you would just flip it and list the vertical direction before the horizontal. So in this case, you would list north before west. But when you always do y over x, you're always going to end up comparing horizontal then to vertical. Okay, so last thing we need to do is write it in sig figs. Our significant figures here for everything is 2. So the total displacement of the person is 260 kilometers west, 39 degrees north. Okay, I just want to say one more thing before the video is done. It seems really arbitrary in this video that I've carried those directions through. But remember, if you get two displacements that are going in opposite directions, it becomes really important to know the directions of those x components and y components so that when you're adding them together, you make sure that you are adding two components that are moving in the same direction. Remember, if they're not moving in the same direction, then we have to make it negative and switch that one so it's in the same direction as the other one to be able to actually add them together. Okay? See y'all tomorrow.